friends, welcome back to my channel. So in today's video we will take some very important reagents, organozinc compounds, as well as we will take organocopper compounds, which are also very useful, and the very important part of organocopper compound is Gilman reagent. So we will take its properties, important properties basically. So first I will take organozinc reagents. First important point about organozinc reagents are they are less nucleophilic as well as less basic than organolithium and organomagnesium compound. This is very important point, right? Because of their lesser reactivity, they sometimes need more reactive reagents along with them. As we will see it later, that with organozinc compound we can also use copper, right? And copper can increase the reactivity of organozinc reagents, so it is very important part. Then how we can synthesize organozinc compounds? We can use zinc, and we can use different type of halides: alkyl, aryl, allyl, halides, and these all halides react under different conditions, right? For example, alkyl reaction of alkyl and aryl halides need some catalyst for their reaction. Otherwise, allyl halides can simply react with zinc powder. Then third point, which is also very important, is reactivity of different organozinc compounds. For example, suppose I am using alkyl or aryl organozinc compound, and we want to react them with, suppose, aldehydes, then we have to use some Lewis acid catalyst. Otherwise they will not react, or their reaction rate is very slow. And if we are using allyl organozinc compounds, or if we are using a organozinc compound which contains some unsaturation near it, right, then their reaction with aldehyde doesn't require any Lewis acid. They will react as such. Their reaction rate will be fast. They don't require any Lewis acid catalyst. So we will see all these things in our examples. So first example is very important, that we are taking here aldehyde, and we are using alpha bromoester. This is ester group, and on its alpha carbon we have halide group attached, bromine attached. That is why it is called as alpha bromoester, and we are using zinc here. So this reaction is called as Reformatsky reaction. And how does it take place? That first this alpha bromoester will react with the zinc, and it will form a organozinc compound. The zinc will be inserted in between alpha carbon and bromine. Then we will use our aldehyde. Then this bond can easily break, and this carbon will attack on this one. This bond will shift on oxygen. So what we will get here, this oxygen having negative charge now combined with this ZnBr, then this bond will break and we will get carbonyl group attached. So this reaction is called as Reformatsky reaction, right? Similar to this reaction, we have another example in which we are using allyl halide. So don't be confused this example with this one, this reaction. This is entirely different, and this is the example from GATE examination also. So here we are using a allyl halide group, zinc and a aldehyde. So again this zinc will be inserted in between carbon and Br. So first we will get this one, right? Again the same reaction will take place here. Now this ZnBr will combine here, right? In next step, the lone pair of electron present on oxygen will attack on this carbonyl. This bond will shift here, and this oxygen now again combine with this ZnBr. When this bond come back, this ethoxide will be removed. So what we will get here, we will get a 5-membered ring, right? So this further reaction take place because we have a good leaving group on this carbonyl. If we don't have such type of group present here, then reaction can stop at this stage only, right? Then we will take the mixed copper zinc compound. As we have discussed in the starting, that organozinc compounds are very less reactive, their reactivity is less, they are less nucleophilic, less basic in nature, and if we do their mixing with copper compounds, then their reactivity can be enhanced. So you can see such type of example, that first they are using zinc chloride, then CuCN.2 LiBr. You can see such type of example, and in this case this zinc will combine with this copper cyanide group and then it will react with this electrophile. So don't be confused with such type of examples. In organozinc compound we have to insert zinc in between carbon and Br. This time we will also insert this part, right? Now this can attack on this electrophile. We have acid chloride here. They can efficiently react with acid chloride because they have good leaving group Cl. What we will get a ketonic group attached here, right? So the reaction is very simple, but you have to simply use this CuCN only, and the use of this copper salt is that this is increasing the rate of reaction only. Then again I am using this copper salt, but this time we have here alpha beta unsaturated carbonyl. So first we have to generate a organozinc compound because we have halide here, and always remember that we have to use halides when we are generating organozinc compounds. So this I will be removed and this group will attach here, this Zn will attach here, because we are also using this copper salt, so it will also inserted here, right? Then we will react it with alpha beta unsaturated ketone, and remember this thing that it will show 1,4 addition. And how you can remember this part? If you remember that we have discussed copper salt with Grignard reagent in previous video, that we can do effective 1,4 addition if we are using copper salt, right? So one way of remembering this is that you are using again a copper salt, and copper salt generates soft nucleophiles, so they will show 1,4 addition, right? Remember that 1,4 addition is for soft nucleophiles and 1,2 addition for hard nucleophiles. So again this time we have copper salt, so it will show soft nucleophilic addition, that is 1,4 addition. And another way of remembering is this, that zinc is also, we have discussed in the starting of video, that zinc is not so much effective nucleophile and not so much basic, that is why it will act as a soft nucleophile, right? So both of them are soft and their combination will also be soft in nature, so it will show 1,4 addition, means it will attack on this carbon. Simply we will get this compound. Next we have here a allyl halide. So first we have to generate again zinc organozinc compound, this one. Then we are using here a allyl halide. So we know that in case of allyl halide, two type of reaction mechanism can be possible. One is that it will directly, a nucleophile will attack on this carbon and Cl will be removed, right? This is called your SN2 mechanism. And another one is that the nucleophile will attack on this one, this bond will shift here and Cl will be removed, right? This is your SN2 prime mechanism. We have discussed about this in Leiden book summary. So in allyl halides we generally decide that which mechanism will be followed on the basis of structure of your allyl halide, that if it is the carbon which is hindered, on which if we have a hindered carbon, then nucleophile will not attack on that carbon, it will attack on the side which is less hindered, right? If this carbon is hindered, it will show SN2 mechanism, and if this carbon is hindered, then it will show SN2 prime mechanism. So in this case we cannot decide that which carbon will be attacked, because both of them seems to be equally accessible. So remember that when you are using organozinc compounds and allyl halides, it will show SN2 prime mechanism, right? It will show SN2 prime mechanism. So it means, so when this carbon will attack on this one, this bond will shift here and Cl will be removed, so we will get this product, right? Then next example is when we have a chiral center next to our carbonyl group, then what we should do, that first we have to generate this organozinc compound, then it will attack on this carbon, right? So you can get two types of product here. There are two possibilities, right? That we can get syn product or we can get anti product. And now you know that how we can decide which type of product will be followed. You have to apply here Falkenhayn model or you can use Cram's model, right? On the basis of these two models you can decide which product will be your final product. So try this one. In this particular case you will get higher amount of syn product. This will be your major product, right? But try to do its try to find out its structure using these two models. Then we will take allyl organometallics of boron, silicon and tin. This is very important part. But before this, I want to tell you here one thing, that if we are using dialkyl zinc compounds, they will provide us, suppose we have this type of zinc compound, they will provide us this ethyl group, suppose, right? So this ethyl group will directly attack on our electrophile. This reaction is similar to the use of this monoalkyl zinc compound, but only difference is they are more reactive than monoalkyl zinc compounds, right? More reactive. Then next part, we have to find out that which type of product we will get using different allyl organometallic compounds. So this portion is important from the point of view of stereochemistry, right? So we will discuss some very important points here, that how we can decide which type of product we will get as a major product. So first we will take a basic example, that suppose we have a aldehyde here and we are using a allyl organometallic of boron, silicon and tin. So suppose I have a substituent present on my suppose we have this type of structure, this is my allyl group, we have a substituent here, this is not necessary, we can have it or not, and we have here a metal with ligands. The metal can be boron, silicon and tin, right? So if we have R here, then first we will take mechanism that we have discussed. So mechanism will include the formation of beta carbocation, means this bond will shift here and it will attack on carbonyl, right? So we will get a intermediate like this, in which we have a beta carbocation, alpha carbon, beta carbon, and then this bond will break and we will get, and here suppose this part is R dash, I will tell you how we can attach this R dash, and when this bond will break we will get this type of structure, right? So this is about general mechanism. Let's come back to the main example here. So in this case we can have two type of products. Suppose this is R dash, we can get syn product or we can get NT product. So this is syn product and this one is NT. Then how we will decide which product will be our major? For first we will talk about allyl borane compound, right? And if you have E allyl borane, then you will get NT as major product. If you have Z allyl borane, then you will get syn as major product. Similarly, if you have E allyl styrene, then you will get NT as major product. Again the same thing will be applied, and for Z you will get syn as major, right? So how we have decided that E will give me NT or Z will give me syn, right? You can remember this one, but you should know how it is applied. For example, in this case we have here a E allyl borane, right? And we are reacting it with this aldehyde. So first thing we have to do, that we'll draw this structure as such first, because this reaction involves a cyclic transition state. So we will try to find out that what will be the structure of its transition state. On the basis of that transition state we can find out the final product. So first we will draw it like as it is, then we will draw a chair like structure for it, and now we will try to fit this aldehyde in this chair like structure, that this is my carbon, this one, and this substituent present on this aldehyde will always be placed in equatorial position. Carbonyl group will go like this, right? So this will be the structure of intermediate. Then in reaction what happens, that this bond will shift here, this will shift here, and it will form OH, right? And these two are NT to each other, right? So in the final product we will get these two groups NT to each other, right? Let's try to find out this for Z allyl borane. Again we will draw it as such, then again we will try to draw a chair like structure, and this pH again occupies the equatorial position and carbonyl will go like this. Now in this case, this Me is in axial position and this OH is in pseudo equatorial position, right? If you break this bond, we have a new bond in between these two carbons and it will form OH, right? This OH is in pseudo equatorial position and this Me is in pseudo axial position. So in final product they will be cis to each other, right? At 1 2 carbon they are axial equatorial, means they will be cis to each other, right? So in this way you will get Z syn type of product from Z allyl purine. Same type of cyclic structure can be drawn for organosthenane compounds. Sthenane means you will have tin here, right? So we have E allyl sthenane here, so it will give me NT product, NT as major product, right? You will also get some amount of syn product, but NT will be your major product. How we will draw its structure? Suppose OH is going above the plane, then this methyl will occupy below the plane side, right? Next we will take reaction of gamma substituted allyl silane with carbonyl. This is nothing different from these organoborane and organostene compounds. They are also gamma substituted. Gamma substituted means this is your alpha carbon, this is beta and this one is gamma. So at gamma position we have a alkyl group, right? So these all are similar to this one, right? So don't be confused with its name. This is all again a substituted allyl silane, we should say it. So it will react with carbonyl, but this time we cannot say that a Z alkene will give me syn product as a major or E alkene will give me NT as a major product. So again we can have syn or NT product as a major, right? But this time you will see that here we are using a catalyst, Lewis acid, that is titanium chloride is used, or other type of Lewis acid can also be used. We will see them later. So in this particular case, E alkene, or you should say that E allyl silane, are more stereoselective, are better stereoselective than Z. Means both E and Z will give syn as major product in both cases, right? But the ratio of syn is higher for E allyl silane than Z allyl silane. That how we have decided that syn will be major, we will see it a little bit later. But first we will try to find out the structure of syn and NT product. So again it will involve beta carbocation as an intermediate, that this bond will shift here and we will have this one as an intermediate and this carbon will attack on aldehyde. We have discussed about this role, the role of this beta carbocation in very detail in Claydon book summary, right? So if you want to study that part, then you can go there and watch that video, right? So first we can have these two type of products, syn and NT, right? Then this involves a different type of transition state, that we have to first draw this double bond, this pi bond, and Me will be placed, suppose like this. On this carbon we have one hydrogen, it will go like this, and on this carbon, this one allylic carbon, we have trimethylsilyl group. It will go away from this cavity and this hydrogen will be placed inside this cavity, right? Next thing we have to do, that we have to align this double bond of this CHO group like this, and H will be placed towards the cavity side and this propyl group will go away from it, right? So this transition state involves 180-degree alignment of both these double bonds. Now what happens, that this bond breaks, this one breaks, and this carbon attacks on this carbon, right? So it will directly interact with this carbon, then this bond will shift here and OH will be formed. So the alignment of this Me is similar to this one, right? The alignment of this Me and this OH, newly formed OH group, is same in the product. It will go on the same side. That is why we will get syn as major product in both cases. Either we have E alkene or we have Z alkene, we always have to place these double bond like this. Trimethylsilyl group will go from the away side from this cavity. These two hydrogens should be close to each other and this group attached here will go away from this cavity to avoid hindrance. We will see one more example based on this one. For example, in this case, right, so we will try to draw this structure similar to previous one, that first we have to draw the double bond in a straight line way, then we will place this Me group here and H here towards the cavity. H will go towards the cavity and Me will go away from it. On second carbon, this is second, suppose this Me will go away from cavity and the next carbon will come like this, then this trimethylsilyl group will go like away from this cavity, and on this carbon we have this ester group attached, right? Here we have hydrogen also. Now we have to place the double bond of this carbonyl group. H will go towards the cavity, again you will get this methyl and OH on the same side, right? This newly formed OH will go on the same side. That is why sin will be major always. So this is very important. Remember the case of allyl silane compounds. So in this case we are using BF3 as a Lewis acid. So this point is also very important, that when you have chiral center next to this carbonyl group on alpha carbon, if you have chiral center, then you have to consider the type of Lewis acid used in the reaction. So for example, if you are using boron compounds as Lewis acid, then you will have to apply Cram's model or Falkenhayn model, right? And if you are using titanium chloride, zinc, tin chloride, magnesium bromide, right, then you have to apply chelation model. But in case of chelation model, you should also have a heteroatom present on this alpha carbon atom. It should be chiral, as well as you should have a heteroatom present on this carbon center, right? So these things are very, very important. You have to consider all these things. So we have taken all the important points regarding this organozinc compounds. Now I hope you can do all the reactions related to organozinc compound, and if you have any problem you can ask me. Then we will take organo-copper compounds, and out of these organo-copper compounds, Gilman reagents are very, very important. Gilman reagents are lithium dialkyl cuprates. We have also discussed other organo-copper compounds with zinc, which we have synthesized with zinc, right? So these are also organo-copper reagents, and this one is very, very important, that I want to tell you some important point about this Gilman reagent. That first point is, it is soft in nature. It will act as a soft nucleophile, means it will show 1,4 addition with alpha beta unsaturated compound. So we will take one example here, that in case we have alpha beta unsaturated compound, so we are using here lithium dimethyl cuprate. So it will ultimately provide me Me minus as a nucleophile. This Me minus should attack on this carbon, this bond will shift here and it will shift on oxygen, and when it will come back, this carbon will take proton and it will form carbonyl, right? So we should get a product like this. We should get this type of product. Now what about the attachment side of this methyl group? It should go above the plane or it should go below the plane. So we have discussed in Claydon book summary that in case of transdecaline, we can decide the attacking side of incoming nucleophile on the basis of group attached here, right? We have seen there that if we have transdecaline, then in that case, if we have hydrogen here attached here, then incoming nucleophile will approach from the axially, always attack axially, right? And if we have methyl here, then it will attack from the equatorial side, right? This is for the transdecaline. So same thing can be applied here for this cisdecaline type structure, that suppose I want to draw this. So in this case, methyl is present here. This is suppose double bond. It should be straight line, but we can understand by this. Then we have carbonyl group attached here. Here we have one hydrogen and on this carbon we have this ester group attached, right? So because we have methyl here, then the incoming nucleophile, that is also a Me minus, will attack from the side equatorial, right? And when it attaches equatorially, then we have, suppose this is 1 carbon, this is 2 carbon, then at 1 2 carbon we have 1 methyl axially placed, 1 methyl equatorial placed. This one go equatorially, this is axially placed. So axial equatorial means they will be cis to each other, they should be cis to each other, means we have this methyl group above the plane also, because this one is above the plane, so both of them will go above the plane, right? So in this way you can find out its structure. Then we have one more example here. So again we have alpha beta unsaturated compound. We are simply using lithium dibutyl cuprate. So this butyl group should attack here, means 1,4 addition will take place. So we will have this type of product, right? So it will give me 1,4 addition product, which we have discussed here also. But in this case we are using a Lewis acid. So you can have examples in which Lewis acid is also given. This Lewis acid is used with some less reactive alpha beta unsaturated compounds, and you can also have trimethylsilyl chloride, right? So when we have this type of Lewis acid present, then it will definitely give me 1,4 addition as major product. Otherwise if you are not using them, then you may also have 1,2 addition product, right? Small amount of 1,2 addition product may also be present if we are not using Lewis acid. So don't be confused with the presence of these Lewis acid in examples. Then next example is very simple, but I have taken here only to explain you that this type of organocuprate compound can also be possible. So simply it will show 1,4 addition and this group will attach like this. The next example is very interesting, that first it will show this organocuprate compound will attack on this carbon, and this bond will shift here, this will shift on oxygen, right? So here I have lithium also, so this lithium will form a stable enolate with this oxygen, right? So it will remain as such, and this group will attach to this carbon, right? In next step I am using a allyl bromide. So this time this carbon will attack on this one and Br will be removed, right? So this is about the stereochemistry of this product, that the attachment to the 1,2 carbon will be trans to each other. The trans will be major product, means if this group is above the plane, then second group, the incoming group, will go below the plane like this, right? These will give me trans product. So we have to decide it, that which type of product we will get on the basis of our substrate, right? For example, in this case we will decide that how these groups will attach. That main purpose of this example is how to decide the stereochemistry of final product. You have to consider only few basic things, that suppose first you have to draw this ring in chair form, and when you draw it in chair form, you know that this group, this bulkier group, will always occupy the equatorial position, right? And at third position we have this carbonyl group. So 1 2 3, this carbonyl group will go like this, and I will place a double bond here. Again I will say that it should not be so much tilted, it should be straight in nature, but we can draw it for our simplicity. Then we have one methyl group attached on this carbon, so this methyl group will also occupy equatorial position. Always remember that when you have a starting compound, that it always tries to occupy most stable structure, and we know that it devoid to have axial interaction, so it groups always occupy equatorial position, right? We have here methyl group, so it will occupy equatorial position, and here we have this chain, so this chain can be written as R, it will also occupy equatorial position, right? Now we have nucleophile, this is Me minus, so this nucleophile will attack on this carbon, this bond will shift here and this will shift on oxygen. This is the reaction. Now our equatorial position is already occupied, So this methyl group will attack axially. It will go like this, it will shift on oxygen, right? So in your product, now we will again draw it in this form. So we have methyl here, and at this carbon, this is third carbon from this is 1, 2 and 3. Here we have one group equatorially placed, and this methyl group will go axially, right? So at 1, 3 carbon, when we have equatorial axial, means they will be trans to each other. For 1, 2, equatorial axial means cis, and for 1, 3, equatorial axial means trans. So if I place this group below the plane, then at third carbon, that is on this one, this methyl should go above the plane. It should be trans to this one. Right, now I can draw this my R part like this, right? And when this negative charge will come back, it will attack on this Br. So I will get a six membered ring here, right? This methyl will go above the plane. Now what about the stereochemistry of this methyl? So if you have seen here that this methyl group was in the equatorial position in the starting, in pseudo equatorial position, because it is next to this double bond, so it was in pseudo equatorial position. So when we have the final compound, then this equatorial and this methyl is in axial position. This was in axial position, and this methyl is in equatorial position, which we will attach here. Suppose in the starting I will take Me like this, that we don't know what is the attachment site of this methyl group, and it was in equatorial position. So 1, 2 carbon, at 1, 2 carbon we have groups axial and equatorial, means they will be cis to each other, means it will go like this, right? So we have used here some very basic concepts, and then we can decide what will be the stereochemistry. So there is no difficulty about this. If you will try to remember it with some very hard rules, then it will be difficult to you, but try to remember only the simplest things, then you can easily do it. That always try to draw such type of structure in chair form, and then placed group in the starting in equatorial position, that was the most stable form, and then attack your incoming nucleophile. And remember that in case of your cyclohexanon or your transdecaline type of structure, axial attack is always favorable. That point we have also discussed in Claydon book summary, that axial attack is always favorable, right? So these few things if you can remember, then you can easily do these things, this stereochemistry part. Then we will take reaction of alkyl halides. So we have seen that our organo copper compounds can react with alpha beta unsaturated compounds, which is very obvious reaction. Next part is reaction with alkyl halides, and this reaction is called as Corey-House synthesis, right? So what is the reaction? That's simple, this I will be removed and this whole part will be attached here, right? This halide will be replaced by nucleophile, they will be replaced. So in this compound, in this we will get this product. So we have taken here 3 different type of halides to determine the type of stereochemistry we will get. So this one is simple because we have not any stereochemistry is given in the starting material, so we have this type of product. What about this example, that we have a secondary carbon and having Br as a halide, then we are using lithium diphenyl cuprate. So it will ultimately provide me pH minus, right? We know that it will provide me pH minus and it will attack on this carbon and Br will be removed. We should have a product like this. Suppose in the starting I am attaching this as such. But what about the attachment sites? So this pH will go below the plane and H will come above the plane. Means there is inversion at the carbon center. Inversion means this reaction is of SN2 type. So whenever you have alkyl chlorides and halides, you will get inversion in configuration. When you are using iodide here, then you will get racemic mixture, because in case of iodide compounds, the reaction is not through SN2 mechanism, it follows electron transfer mechanism, right? So remember this case, that in case of iodide you will get racemic mixture, otherwise you will get inversion in configuration. Then in case of alkenes, we will have retention in configuration. E will remain E, Z will remain Z. So there is retention in configuration. Next is, we can also have triplates. In addition to halides, we can also have this such type of reactions with triplet. Means in this particular example, only this triplet group will be removed and we have methyl attached here. We are using here a mixture of Grignard reagent and copper iodide. This is not simply our organocuprate compound. We are synthesizing it using this Grignard reagent, right? Then this is very interesting example that we are first generating a different type of organocuprate compound using this lithium diethyl cuprate with this acetylene. Then we will use it with halide. So first reaction is the reaction of this lithium diethyl cuprate with this acetylene. So if you remember, if you can see that this with this copper compound we are using two alkyl groups, right? So we also need two acetylene here for this exchange. So simply this ethyl will attach with one carbon, right? And this copper lithium group will attach here. We need two of this to maintain the valency. We need two of this group, right? And this addition is, I am attaching this ethyl group and this copper lithium group on the same side. So this addition is syn addition. This is very important to determine the final stereochemistry of the product. Then we are using this alkyl halide. So simply I will be removed and this group will attach with this I. So we have the stereochemistry is maintained, right? So these two hydrogen will remain on the same side, ethyl will remain on the same side. Simply this carbon will attach with this carbon from the same side of this copper lithium, right? So this one will be the final product. So you have to simply remember this syn addition. The addition will be of syn type and this group, this alkyl halide will attach from the same side of this copper lithium, right? Then you can decide the final product. Then we will take one more example which is very simple, that we are using acid chloride here. So this organolithium compound should replace this Cl. We have seen till here that alkyl halides can show exchange reaction with this organocopper compounds. So Cl will be removed and this this butyl group should attach here. But here we have acid chloride and in final product we will get ketone. So this reaction is highly chemoselective for acid chloride. For acyl chloride, this reaction is highly chemoselective. It will not react with ester, ketone or any other group attached here, nitriles, ester group attached. It will not react with that. If you have alpha beta unsaturation, then it will react definitely. But if you have ester group, nitrile or simple ketonic group, it will not react with that. It will simply react with this acyl chloride. So it has highly chemoselectivity for this acyl chloride group, right? Then we have last and very simple and interesting example here, that we have epoxide ring opening using this organolithium compound. So we know that how we can open epoxide ring. We have to break this carbon between oxygen and carbon. Now question comes, which bond will be break? Always this organocuprate compound will attack from the less hindered side. First point is this, which is very obvious, and it is also for all the type of epoxide reactions except when this oxygen is activated, right? We have discussed the reaction of this activated oxygen and simple epoxides in Claydon book summary in very detail. And second point is, this reaction will be SN2 reaction, means inversion at this carbon. So in final product, this carbon was previously attached with above the side of this oxygen. This carbon is previously attached with this oxygen and this was above the side. So this propyl group will attach below the plane like this, right? And on this carbon stereochemistry will remain as such. Here we have OH. So inversion only at this carbon, right? So remember only these 2 points, then you can easily do this part also. So I think I have taken all the important reactions of this organo-copper compounds. In next part we will take questions related to this chapter. The other portion of this chapter are the reaction of palladium and chromium compounds or complexes, but I will not take it here because I have already discussed all these reactions of all the important reactions of palladium compounds in my videos on organometallic chemistry, right? So if you have any doubt you can ask me, but first you have to watch that videos. I have discussed all the important parts required for net and gate examination in organo in that series, so you can watch that first. Then if you have any doubt then you can ask me, but in next video we will cover all the problems given in the chapter and related to this chapter, right? So thank you so much for watching. If you like my videos please share it with your friends. Thank you.